All right, so let's have a look through the multiple choice. All right, so which one of the following DEs is y equal to x cos x a solution? So I guess the simplest way is use our CAS. Differentiate x cos x gives me that. If I then differentiate the derivative, there's dy dx. Okay, so there's d squared y dx squared. And so then just looking at the options, they seem to add the first derivative to the function. So, sorry, the second derivative to the function. So there's my second derivative. I guess in blue, if you like, is the function. I added the function. And I end up with a negative 2 sine x. So the second derivative plus the function is negative 2 sine x. So we get E as an option. All right. What about number 2? So it's a rates question. So the rate of increase by reproduction is K times the number of bacteria present, where K is positive. They're dying at a constant rate, so we have an increase and a decrease. So the net rate, okay, is the rate of increase minus the rate of decrease, or the output rate. So what's the rate of increase? It's K times the number of bacteria present, so Kn, whose N is the number of bacteria present. So Kn is my increase. They're dying at a constant rate Q bacteria per day. So we didn't actually have to calculate it. We just know that Q of them are dying. So the actual rate of change, I've got Kn increase minus Q dying. So there's my dNTT there. Okay. Similar, we want to know the rate the volume is changing. Water is coming in at a rate of 0.5 meters cubed per hour. It's a rectangular prism. Okay, at the same time water is flowing out through a hole at the bottom, so it's flowing out at 0.1 V meters cubed per hour. Again, what's the model? So the volume, it's not like we've got a solution in there we're worried about, it's just water coming in, water coming out. What's the rate of change of the volume? So the input rate minus the output rate is going in, up by 0.5 meters cubed, it's decreasing by 0.1 root V cubed per hour. So the difference is going to be my rate of change, which gives me option B. Let's have a look here. Question 4. Okay, we've got a salt solution this time again. Q is the amount of salt. Typically, we use Q as the amount of salt in the tank. So what's the rate of change of the amount of salt? So the input rate minus the output rate. What's the input rate? So I've got 2 grams of salt per litre at 5 litres per minute. So there's my 2 times 5. So I've got 10 grams of salt per minute coming in. The rate that it leaves us, okay, it's the concentration of my solution times the rate at which it's leaving. So we can see the rate at which it's leaving is 7 litres per minute. The concentration, well, it's just how much salt there is divided by the volume of liquid. So what is the volume of liquid? So we're leaving at 5 litres. We're flowing in at, we're leaving at 7 litres. We're coming in at 5 litres, which means my volume of liquid is changing by 2 litres per minute. So there's my minus 2T. So the volume of the mixture is 50 litres less 2 litres for every minute. So Q over 50 minus 2T times 7 gives me the output rate. So there's my DE as in its entirety, and that must match off to option D. All right. Euler's method, so it's about identifying the key things, isn't it? So the derivative is equal to natural log of x, so there's my derivative. My variables are x and y. At x equal to 1, okay, y is equal to 2, so that's those two values. I need to know at x equal to 1.2, so I'll just go up to 1.3. So from 1 to 1.3 with a step size of 0.1. So 1.2 is the value I was interested in, and that's 2.0095, option B. All What else have we got? We've got another DE, find the solution or the equation that models this solution. So same sort of thing. The second derivative is equal to 5 times the first derivative minus 6 times the function. So let's work that out. Second derivative, first derivative, ke to the kt. The second derivative, k squared e to the kt. So if I put that in, if you like, there's my second derivative, k squared to the kt is equal to the first derivative, 5 times the first derivative, which is here, minus 6 times y, which is there. And I want to solve that for k. I get k is equal to 2 or 3. So really, let's opt for our CAS at every opportunity. All right. Another Euler question. This time the step size is 0.2. So step size of 0.2 is the last thing we put in. The initial condition at x equal to 0, y is equal to 1. So at x equal to 0, y is equal to 1. And we're interested at x equal to 0.4. So I'll start at 0 and go to 0.4. We said our step size was 0.2. Make sure your rule is put in correctly. Obviously that was the first little trick here. What was dy dx equal to? So we had to rearrange, yeah. And so at x equal to 0.4, we get that 1.3961, which is option C. 9, a jug of water, temperature is placed in a refrigerator. That looks like a Newton's law of cooling. Okay, so from our notes, we know that Newton's law of cooling. So the temperature inside the refrigerator is maintained at 4 degrees centigrade. When the jug has been in the refrigerator for T minutes, the temperature of the water in the jug Y is Y degrees. The rate at which the water's temperature decreases is proportional to the excess of its temperature over the temperature inside the fridge. In other words, it's proportional to the difference. So the difference of the temperature of the jug Y minus the temperature of the fridge is just Y minus 4. Because it's proportional to that, it's just some constant times that K. Okay. We put in our initial conditions. At T equal to 0, the jug of water was at 20 degrees centigrade. So where does that fit in? So I guess T equal to 0, Y is equal to 20 is only those two. And the only difference between the two, we've got y plus 4 and y minus 4. Clearly it's a difference, so it's C. All right. Another Euler, dy dx is e to the minus x, independent, dependent. At x equal to 2, y is equal to 1. That's what that means. And we want to go up to 2.2, so that's my upper limit, and I'm going up by 0.1. 1.02578. All right, so let's have a look at our slope field. All right, so let's have a think about this. So we're going to work out which of these is the most appropriate DE. So I'm a big fan, as you know, of just picking points and checking to see. So clearly we know that at x equal to 0, the derivative is 0. So if that's the case, at x equal to 0, the derivative is 0, so we can eliminate A. B, at x equal to 0, undefined, that's no good. So really straight away from that point, we've only got two possibilities. All right, and so then really it's just pick another point. So I opted for the 0.11 since they're both positive numbers. So at the 0.11, I should get a negative gradient. So at the 0.11, C gives me a negative gradient, so I'm happy with that response. At the 0.11, E gives me a positive gradient, which doesn't match off to my DE. So C is the correct response. We've got another rate. The rate at which a type of bird flu spreads is fairly topical, isn't it? Through a population of 1,000 birds in a certain area is proportional to the product of the number of infected birds and the number of birds not infected, okay, after T days. So what does that mean? So if I have n infected birds, that means I must have 1,000 minus n non-infected birds. So the product of them, and if it's proportional, k is my proportional constant. Okay, so what looks like it could be, you know, obviously we've got some divisions there. We spoke about a product, so really B, C, I guess those ones could be, but it's that n 1,000 minus n, isn't it, that's really important. So I think C is the one. 13, another slope field. All right, same sort of thing. I picked some values. There's two possible ways we've approached this one. So let's go back to the green pen. At x equal to 0, it looks like my gradient is positive and near enough to positive 1, isn't it? So if I put x equal to 0, I should get a positive response. So if x equal to 0, sine of 0 is 0, so it can't be sine, all right? And in fact, at C is in actual fact in terms of y. So obviously we're saying that as y varies, if we look down the axes, as y varies, the gradient isn't changing. Yeah? And yet that's clearly not the case in C. So that's why we can eliminate C. All right? So it's either cos 2x or cos a half x. So again, we could pick a point. And you can see here I sort of picked at x equal to pi on 2, which is sort of down here somewhere. At x equal to pi on 2, the gradient is negative. So if I put x equal to pi on 2, if I put it in B, I get cos of pi, which is negative 1, which seems reasonable. If I put it into E, I get cos of pi on 4, which is positive 1 on root 2, which is going the other way. So it can't be E for that reason, which is why B is a good response. Okay. The other way to consider it is what I've done here in red, is just followed a line and drawn a possible solution. And clearly from the graph, okay, we've got a sine graph and its period is between negative pi on 2 to pi on 2, so the period is pi. Which of these particular derivatives would give me a function, in fact a sine function with a period of pi? Well, since we're looking at the derivative, it's got to be a cos something. And only cos 2x is going to give me a period of pi, isn't it? A sine function with a period of pi. So either option is reasonable. I guess I prefer to substitute points in as opposed to trying to come up with a rule for the actual equation. 14, we've got another rate. What have we got there? Volume in the tank when filled to a depth of h meters is given by V is equal to 4h. So straight away there, I've done a little div dh must be 4. Water flows into the tank at a rate of 0.2 meters cubed per minute. So meters cubed per minute suggests that it's an input volume. So div dt, 0.2, and leaks out a rate of 0.01 h meters cubed per minute. Okay, the differential equation which when solved would enable h to be expressed in terms of t. So I need h is equal, so I need a dh dt. There's dh dt. So I need dh dt, so I've got the rate at which the volume is changing, div dt, so 0.2 coming in minus 0.01 h coming out, yeah? So dh dt is dh dv div dt. Okay, so div dh, so we've skipped a couple of steps here. So let's tidy up my div dt first. So div dt is equal to, what's that, 1/5 minus root h on, well, 0.01, 100, which is equal to 20 minus root h on 100, isn't it? Okay, so that's dv dt. I'm going to multiply that by dh dv, which is 1/4, which gives me my 20 minus root h over 400. So that's where that 400 comes from. Which, if we look closely enough, is my 20 minus root h over 400, which is C. All right. And I guess the key being then, don't forget that's what dh dt is, which is the dE I need to give me h in terms of t. All right, another Euler method. Okay. So this time though, we've got the answers expressed, they haven't been evaluated. So whilst you could certainly go to your CAS and then evaluate each of those responses and see which decimal matches off, we might just need to take it a step at a time. So again, what have we got? We've got the derivative, tan inverse of x plus 1, step size of 0.2, y2. So we know I have to do 2 steps. So y1 is equal to y0 plus 0.4 times well, hang on, 0.2 times, here we go, 0.2 times 2 tan inverse of xn plus 1, yeah? So h times dy dx. So 0.2 times 2 is my 0.4. If I put xn in there, which is x0, I get tan inverse of 1. So I get 1 plus 0.4 times tan inverse of 1. That's y1. All right. So then y2 is all of y1, which is there, plus 0.2 times 2 tan inverse of, with x1 substituted in, which is 0.2. So that's 0.4 tan inverse of 1.2. So tan inverse of 1 is pi on 4. So there's my pi on 4 there, times 0.4. So if we sort of tidy it up a fraction, I'll get 1 plus 0.4 pi on 4, which is 0.1 pi, plus in green there the 0.4 tan inverse of 1.2. So if we look for something that looks a bit like that, we get D. All right, so there's one there that I guess it's one way of making sure, or we're trying to ensure that you actually know the process. Okay, another slope field one. Again, I prefer to substitute a few key points in. So at x equal to 6, or thereabouts, we have a 0 gradient, don't we, all the way through. So at x equal to 6, which ones give me a 0 gradient? So that one doesn't, that one doesn't, that one doesn't. All right. So then I just picked another point then for the eliminate B or D. So what do I know? At y equal to 3, it looks like it's a fairly vertical line. Okay. And you can tell it needs to be 3 because is it a little bit above 3 or a little bit below 3? Well, we know 3 is meant to be the point. So clearly at y equal to 3, D won't give me an undefined answer, but B will. Yeah, because obviously 3 minus 3 in the denominator is 0. So I think definitely a massive fan of just substituting a few key points in. All right, nearly done with them. So let's have a bit of a read through. A fish tank initially has 4 grams of salt dissolved in 100 litres of water. Its concentration is too high, so we're going to water it down. Okay, so it's tapping off at 10 litres. So let's work out x kilograms, that's a little bit different. X kilograms per litre, so x is the concentration. All right, so let's think about that. So the rate of change to QDT of the amount of salt, which I guess you could argue the amount of salt present, which probably should be x, but that's okay. The amount of salt present okay, at any point in time is equal to the input rate minus the output rate. So the rate of change of the salt, I should say. Input rate is 0, so that's true. Whoop. The input rate is 0 minus, so it's the concentration times the volume, isn't it? Which is minus the concentration, which we said was x, times the rate at which is leaving, which is minus 10x. So dq dt is minus 10x. So the amount of salt present, okay, so if we think about the amount of salt present Q, I've got 100 litres of water times the concentration, which is just 100x. Yeah, so then dq dx is equal to 100. So now if I want to know, looking at the series of dEs we've got to choose from, they're all dx dt, so I've got to find a dx dt in here. So that's the rate of change of the concentration as opposed to a rate of change of the amount of salt present. So dx dt, just dx dq dq dt. Dx dq is 1 on 100 times dq dt, which we worked out to be negative 10x, which is negative x on 10. So what we're saying is dx dt is equal to negative x on 10. So we've got a few different equations that sort of look like that. So just to make it obvious, if I put the negative 10x on 10 across to the left-hand side and then multiply everything by 10, I get 10 times dx dt plus x is equal to 100, which is A. Okay, so it's a little bit different, that one, but we just got to keep thinking about what the variables are and what they want us to measure. So let's have a look at 18. What have we done there? Another slope field. All right, again, let's pick some few key points. What have we done? So at t equal to 0, dv dt isn't 0. We can see it's clearly a it's got some negative gradients. It's 0 at the start, but it's not 0 everywhere. So if t is equal to 0, which means kt squared must go. All right. Let's think about the green ones. So if dv dt is less than 0 everywhere, isn't it? We've got a negative slope everywhere. So if dv dt is less than 0 everywhere, that means k on v is no good to us, and kv squared is no good to us. So that brings us down to either C or E. Okay, negative kv squared is negative everywhere, so that's a possibility. A negative k on v is negative everywhere. So whereabouts is the volume 0? The volume is equal to 0 along here, and my gradient is 0 there, isn't it? So if the volume is equal to 0 and the gradient is 0, that rules out E, because here it's undefined, so we must have C as an answer. All right. 19, another Euler. What have we got? We've got dy dx equals, so there's our dy dx, comma x, comma y. At x equal, we've got the point, at x equal to 0, y is equal to 2. Step size of 0.1, y1, okay, so we've got y0 here, y1 here. So 2.2 is going to give me the answer that we're looking for. All right. Another DE, this time we're solving it. So I went to the CAS here. The amount of a drug remaining in a patient's bloodstream, 2 hours of drug has been given, is given by that DE. So I just solved it. So DE solved, we've got x dashed is equal to negative 15 on 100. So because we've got exact answers here, put exact values into the DE. If you put 0.15, well then you're going to get decimal equivalence. So a possible DE, okay, is there, oh, sorry, a possible solution, and we want to know how long it takes to halve it. So C3, that's my initial amount present. So if I put C3 on 2 out the front, equal to C3 e to the negative 3t on 2, or even if you put a half out the front and take away the values, it's okay. We get 20 log natural log 2 on 3, which is 20 natural log 2 on 3, which is B. All right, we've got 2 more before we go short answer. Another DE. All right, so let's pick some random points. So 2 ways. What have we got? At x equal to 0, we get a positive gradient. Yeah, all the way along at x equal to 0, we've got a positive gradient. So if x is equal to 0, we get a positive answer. So what does that mean? If x is equal to 0, I get negative 2y on 2y here, so that's no good. At B, if x is equal to 0, I get 2x over negative 2x, so that's negative, so that's no good. At y equal to 0, I get a negative gradient. So at y equal to 0, I get a negative gradient, so that could be a possibility. At y equal to 0, I get a negative gradient, that could be a possibility. At y equal to 0, I get a negative gradient, which is no good. So I'm down to A or C. What do I do then? No, just pick another point. So you can sort of, I've gone for where it's vertical. So maybe, what's that point? I guess we're over here somewhere now, aren't we, where it's yellow. So we can see that it's sort of around, even if I pick this point up here, at negative 2 and a bit, 1 and a bit, we should get a 0 on the denominator. So I've gone for negative 5 on 2, 3 on 2. If I substitute that into A or C, only A will give me the 0 on the bottom. Okay, I could have confirmed the same thing maybe up there. The point 3 on 2, 3. Okay, which is, I've got negative 3 on 2, which is the equivalent point there to this one here that I checked, or up there, and again try to get a 0 equation. All right. So again, just substituting key points in. Finally, as I sort of mentioned, the question should read dx dt is equal to negative 10 on 10 minus t. So there's my derivative. My variables, independent variable is t. X is equal to t squared, so the t is the independent. X is dependent upon that. I'm interested in my initial condition at t equal to 0, t is equal to 5. Oh, sorry, x is equal to 5. And I want to go as far as 1, going up in a step size of 0.5. And we get 3.97. B. Okay.